All right, as far as I know, I am now recording this and I will post it. So it ran like, I hope I don't run more than an hour. I hope I don't. We'll see. Um, for today, um, here are the notes that I'm going to work from, and I will open this up. Again, I encourage you to have a piece of paper handy. If you can print these real quick. There we are. Oh, I already had this. Close that, maybe. Okay, there it is. This is what I'm going to be doing today. I want to talk briefly about the topic questions. I want to do an example of each that you're going to see from 210. And then I want to get into uh, doing an Euler's approximation of this particular equation. And I'm going to layer that with doing a slope field and doing separation of variables, integration, and there's a whole bunch of stuff packed into this one little example. The Euler's approximation is something that's actually showing up in your ebook. It's one of the set of questions you're going to see on Sunday's assignment. More pressing, I would imagine, are these topic questions, which are today. All right, so 610 is basically the application of the first fundamental theorem of calculus. There are two. The first one I think is that the derivative of an integral returns the original function. This is the complementary fundamental theorem. It's that when you have a definite integral, well, there it is. From A to B, you have a function that's the integrand. If you do the antiderivative of that, you apply it for B, and you subtract the value for A, and that's the fundamental theorem. The examples that you're going to see on the topic questions, I cannot do a better job than Kim Thomas did on her videos. They are on point. It's almost like you could take her questions, change the numbers, and get the answer, which doesn't mean you understand it, but that'll get you the short-term fix. 6.9 is about U substitution. We've been doing this for at least a week. I'm going to say 2 weeks now. And the types of questions that you're going to see is there are 6 questions. One pair of them is going to involve an inverse trig function. Another pair of them is going to involve you using a power rule. And another pair of them is going to involve you doing a natural logarithm. Now, what that means is you've got to sort of deconstruct the question. You got to find a way to make whatever the integrand looks like. You got to format it so it fits into an inverse trig rule or a power rule or a natural log rule. And again, we've done enough of these. I'm gonna suspend doing an example of these. I guess maybe at the end of class, if you want one in particular, I could take requests. What I was going to focus on though today was this process. This is Kim Hires is doing these. This is an integration technique called long division and completing the square. It's really a review of algebra 2 back when you did long division of polynomials and you did completing the square of polynomials. The calculus is very minor in this. I guess maybe the biggest thing is just recognizing that you have to use long division and recognizing that you have to use completing the square. So let me cut right to it. This is where having a piece of paper would come in handy. What we're going to do is I'm going to rip up this Word document because I want to make some room. I'm going to do the first one, which this is an example in which you're going to be using long division. So let me give myself some space here. All right. All right, that should, I think even I should be able to write in this amount of space. But I'm greedy, I want more space. All right. Okay, so to integrate this, I mean, you can try to get a U substitution working off of this. It just isn't going to happen. So what you want to do is you want to long division this. So we're looking at the divisor is x minus 3. And the dividend, I haven't used that word in so long. Let me get some more space. How much did I? Yeah, I'm okay. I'm gonna get more space. Greedy for space. What can I say? I'm buying you guys time so that you can maybe get this down and start it on your own. When you're doing long division of polynomials, such as this one is, you're going to tend, where you're going to end up if everything goes well and if it's a typical long division type of integral, what you're going to end up with is you're going to end up with an integral in which it's going to be the power rule and a natural log. So there, I've erased everything. So I've got long division wise, I'm looking at x minus 3 divided by x to the 4th plus 2x to the 3rd. Now, if you're doing, I don't know if you know, if you want to do synthetic division, knock yourself out. I taught Algebra 2 one semester and I learned it, I taught it, and I never use it. If I were to, I will always default to this polynomial long division. One thing I am seeing is that we don't have an x squared term. I would suggest that you put in a placeholder such as, how about 0 x squared? And then we got plus 5x minus 1. All right. So we're set up for long division. What I do is I look for what number is going to get me, what number do I have to multiply x by in order to get x to the 4th? Well, I'm thinking x to the 3rd is going to do it. So what it gets me is x to the 4th minus 3x squared. I wrap that up in parentheses and I subtract it away. And what I'm left with is, notice that this is not negative x squared. When I subtract negative 3x squared from 2x, I'm sorry, this should move to the 3rd. When I subtract negative 3x to the 3rd from 2x squared, I end up with a positive 5x to the 3rd. And then I'm just going to rewrite the dividend. I still have to deal with plus 0x squared plus 5x minus 1. Okay, let's do it again. So what do I need to multiply x by to get 5x to the 3rd? I need a 5x squared. So plus 5x squared. So I've got 5x to the 3rd minus 15x squared. And again, you might have learned this a different way from a middle school teacher or Mr. Alioth or someone. This is how I do it. All roads are leading to the same place. So the x to the 3rd terms cancel out and we're left with a positive 15x squared. Pull everything else down. So we got plus 5x minus 1. And let's do it again. This time we're going to need a 15x. And that's going to get us 15x squared. Minus, these numbers are getting big. Minus 45x. Wrap it up so we can subtract it. That reminds me to change the signs. That's why I put that parentheses around it, the negative. So I end up with 50x minus 1. Okay, I think we got to do one more round of this. So we're going to do a 50, multiply 50, not 5. And times x minus 3 is going to get me a 50x minus 150. Wow. Should have written an easier question. All right, regardless, I end up with a positive 149 as my remainder. So plus 149 out of x minus 3. And so what we end up with is an integral. Switch colors here to emphasize. We end up with the integral of x to the 3rd plus 5x squared plus 15x plus 50. That's a 0 there. Plus 149 over x minus 3 dx. All right, and yeah, maybe I should have written an easier question. I don't know. But now we integrate this. We're not differentiating it. That's going to come on Monday or Tuesday. So the integral of this antiderivative, power roll the whole thing through. X to the fourth over 4 plus 5x to the third over 3 plus 15x squared over 2 plus 50x. Here's the one special one. We've got plus 149 times the ln of x minus 3 plus c. Let me double check my answer that I got. X to the fourth over 4, 5x to the third over 3, 15x squared over 2, 50x plus 149 ln of x minus 3 plus c. Yeah, that's it. There you go. That's long division. Again, where was the calculus in this? The calculus occurred when you looked at the integral and you decided on a technique to apply. And then most of this time here has been spent doing an algebra 2 question or pre-calc question of polynomial long division. And then the very end, the calculus occurred when we applied the power rule in one natural log. All right. Any questions? Okay. Let's move on to the next one. This one involves completing the square. And what you want to recognize or look for is you want to look for a quadratic type expression, and it's not factorable. And yeah, quadratic expression, not factorable. Be advised that the questions do have to be rigged for you. There are some situations, there are equations that cannot be integrated. It's just the fact of life with calculus. This one can be, because I wrote it to be integrable. Now, what is that? I made it too wide. You're going to have to wait for later. Okay, I'll just have to deal with that. Okay. Yeah, so basically we're calling on our skills from Algebra 2 and completing the square. So let me erase first. Why don't you guys get started? If you forget, you'll have to wait till I erase and then I'll get you started. Recognize that this is a quadratic in the denominator. When you're successful on this, chances are the rule you're going to be applying to get the integral is going to be one of the inverse trig functions. All right, so erasing is done. Okay, let's go blue. Blue's a nice color. So we've got 2x squared minus 12x plus 26. And if I reference these terms, I'm going to call this one the quadratic term, this one's the linear term, this one's the constant. I don't know if that's totally right, but that's how I'm going to refer to them. One of the things that when you're completing the square is you do not want to have a constant in front of this quadratic term. So we're going to have to factor this 2 out. So I'm going to rewrite this as, and I'm not only going to factor the 2 out of the quadratic term, I'm also going to factor a 2 out of the linear term. So this is going to become 2 times x squared minus 6x, and then leave a little space. All right, and don't do anything. The 26 is just going to bide its time, hanging out, chilling, right? And now we're set up to do our completing the square. And what you want to do when you're completing the square is you look for this coefficient in front of the linear term. You take that 6 divided by 2, and you get 3. And then you take the 3 and you square it, and you get 9. That's going to be your completing the square. So we're going to add 9 to this. Now, we just added 9, and we can't just arbitrarily add something. We got to keep it balanced. We have to add nothing, because that's the only way we can not change this expression, its value. So if we're going to add 9, that means we got to subtract 9. But hold on, we didn't just add 9, we added 9 times 2. So we actually added 18. So to keep this balanced, we're going to have to subtract 18. All right, that's the completing the square part. Now I'm going to write this. I'm actually going to complete the square. We've got 2 times, well, this x squared minus 6x plus 9 becomes x minus 3 quantity squared plus 8. And yeah, what that takes us to is we're now going to write this as the integral of 1 over. And because I'm adding terms, there's no radical sign. What I'm thinking of is where I'm targeting toward is the integral of the inverse tangent. And the integral of the inverse tangent, you've got to get into a 1 over 1 plus x squared mode. And that'll get you to tangent inverse of x. So what we're trying to do is we've got to format this to look like that. All right, well, we've done the first part by completing the square. So I'm going to write this in that format of 8 plus 2 times the quantity x minus 3 squared dx. Okay, I see a 2 I can factor out of the denominator, so I'm going to write this as 1/2 times the integral 1 over 4 plus x minus 3 squared dx. Okay, we're getting there. Now, next on the agenda is we got to deal with this 1 right here. We got to make this 4 look like a 1. So let's factor out again. This time, let's factor out a 4 from the denominator. So my next step, and I might be doing more steps than you guys could have done. Maybe you could have had this done by now, but I'm showing it in all the glorious detail. I'm going to need more space. Okay. So we got 1/2 integral of 1 over 4. Okay, if I factor a 4 away from 4, I'm left with 1. And if I factor the 4 from the x minus 3 squared term, I've got x minus 3, that quantity is squared over 4. My handwriting is degrading, dx. Okay, we're almost home. If I let's factor that, let's get this 4 out of anytime you have a constant, a factor of a constant, you can pull that out of the integral. And I think that makes this look a little bit nicer. So I've got 1/4, and I also had a 1/2. Don't forget that one. 1/4 times 1/2, and we've got the integral of 1 over 1 plus. And allow me to take the liberties of rewriting this. We've got x minus 3 over 2, that quantity squared dx. Okay, that was convenient that we had a perfect square with that 4. Believe me, I knew what I was doing when I wrote the question. So anyway, we are almost home free. The last thing we got to do is I'm going to work my way up the page. And in order to do that, I'm going to get rid of that completing the square work. Oh my gosh, I'm looking at the clock. Hurry, Dan, hurry. Okay, our U substitution is going to consist of this. We're going to get the x minus 3 over 2. That's what we're going to pull out with our U substitution. So our du dx is going to be, did I do that right? Ooh, I'll be darned. I'm sorry, I actually did it wrong on my answer key. We end up with 1/2. So we solve for dx. We got 2 du is equal to dx. Give me a holler if I make a mistake, guys. I mean, I am taping this. I'll rewatch it, and I'll let you know if I made any mistakes post-mortem. But while I'm working live, I'd rather correct any mistakes now if I make them. But okay. Now apply this U substitution. We've got 1/2. We've got 1/4. We've got the integral of 1 over 1 plus, okay, x minus 3 over 2 is our u squared. And then we're getting the dx out and we're replacing it with a 2, should have been a u right there, du. And to really belabor the point, we've got 1/2 times 1/4 times 2 times the integral of 1 over 1 plus u squared du. And what that's going to get us to is, I need an eraser. We're going to have, let's just call it 1/4. 1/4 tangent inverse of u plus c. And I just erased what the u was. So it's 1/4 tangent inverse of, I think it's x minus 3 over 2 plus c. And that is the integral of that. And if you take the derivative of this, you should be able to get home. All right. All right. That completing the square, again, I think one of them that you'll see in the topic question set does have an inverse sign that you're going to have to complete the square for. I know that at least one of them has an inverse tangent. I'm not sure what the third one does. So anyway, there we go. And that'll take care of what you need short term. Welcome, Evan. That'll take care of what you need short term as far as tonight goes. Now let's see where am I on the clock here. I've got till 11:10 and I'm reading it as 10:30. Okay, this is stuff that you will. You guys have any questions? A little sip of my coffee here. I'll edit my slurping out of the recording. Okay, there was some interest in a Euler's approximation, and there's a whole boatload of things embedded in this one. I'm going to start with just showing you the Euler's approximation. I like doing this one because it has a x's and y's involved. And doing Euler's approximation is really a matter of bookkeeping than any sort of mathematical insights. So I'm making some space. And what you're going to need is you're going to need 5 columns. I do pretty exhaustive, detailed notes on the ebook solutions, so I think they should get you home regardless. The way you want to set this up, the first column you want is you want an xy. This is where you're starting. And in this case, we are starting right there. I don't know why they don't just say start at 1, 2, but they always sort of phrase it as y equals 2 when x equals 1. So we're starting at 1, 2. All right, so that's where we start. The next thing you need is you need your dy dx, which is given to you. And for us, there's the dy dx. Then you need a delta x, which is given to you right there. And then you need a delta y. And then finally, what's happening is the x is modified by the delta x, and it becomes x plus delta x. And then the y is modified by the delta y, and you get y plus delta y. All right, so tighten this up a little bit. Let's get started. That should be the, if you were to have a template for how to set this up, what's shown in black is probably be a pretty decent template. We are starting at 1, 2. The dy dx we're using is negative y over x, which in this case we would be negative, and we plug in the x's and the y's into the differential equation we were given. So y is 2, x equals 1. What that means is at the ordered pair 1, 2, this thing has an instantaneous rate of change of negative 2. And you can almost, where I'm going toward by the end is making a slope field. And there's the ordered pair 1, 2 right there, right? And it's, if you were to draw its slope, it would be whatever line is shows up as like -2, right? So the delta x is going to be 0.1. Why? Well, because they told you. That's always going to be given to you with increments of 0.1. So 0.1. Now the delta y, where that comes from is, let me go a little bit of theory here. dy dx is an instantaneous rate of change. If we push 2 points close enough together that the difference between them becomes 0, the slope becomes the instantaneous rate of change. It is the derivative. Before we get to that point, we've got a measurable difference in the heights, and we've got a measurable difference in the horizontal. So this is more a calculus or infinitesimally small fraction, where this is more of a measurable type of fraction. So anyway, that's how we get to the delta. What we're looking for is, where does this delta y come from? Well, it comes from this relationship between the derivative and a non-derivative comparison of slope. So we're going to solve for the triangle y. It's called delta y. It's a Greek letter, that triangle. So we're going to solve for delta y by multiplying both sides by delta x. These cancel out. So the way you get this delta y is by multiplying delta x times the dy dx. So you multiply these two together, take this times that, and that's what your delta y is going to be. All right. So let me cut a little space here so I can get some room. Get that nonsense writing out of there. Okay, so the dy dx times delta x at -2 times 0.1 is -0.2. And now that takes us to the final step in this process. We go with 1 plus 0.1. So our new, where we've moved to is now the ordered pair 1.1. That's our new x coordinate. The y coordinate, we started at 2, and we've now traveled -0.2. So we're now at +1.8. All right, so that's our first iteration. So we're not done because we don't finish until we reach x equal to 1.3. So, and almost all the questions I've ever seen, it's always 0.1 is always your delta x, and usually you have to go 3 iterations. So I'm going to be quiet now. If you guys have any questions, give a holler. I expect you're working along. So I'm just going to let the pen talk for a bit. There's our second iteration. We've now arrived at the point 1.2 for x and 1.6364 for y. We got to do this one more loop. I had to drop a line because my writing is too large of a font coming out of this pen. So I've got my dy dx at this point is -1.364. The delta x, again, it's almost always going to be whatever is given to you. In this case, it's 0.1. So our delta y is negative 0.1364, which is going to get us to our final destination, which is 1.3. And okay, that's nice. I wish I could say I planned this one, but I actually end up with 1.5 as the approximation for this. Okay, so if you watched the video that I recorded, I sent you guys a message yesterday, late evening, about I had made a video that you can watch on Schoology that I basically do what I just did now. I walk through an Euler's approximation. Now this is the second one that has a live walkthrough. And when you look at the ebook assignment, they're not live, they're not dynamic, but you can at least see the work that goes into setting it up and the process to complete it. All right. Okay. Where I want to go to is I said something a little cryptic in the Euler's approximation, the differential equation that I recorded yesterday. I said you can't integrate it, and I'll explain why you can't integrate it when we're in class together next week. But I want to show you why we can integrate this one. So I'm going to lose all of this. I do want you to have written down where we ended up. We're at 1.3, 1.5. So as I get rid of this, okay, I'm going to show you why we can integrate this one. This is what's called separable differential equations. Yeah, if you've got dy dx is equal to, and you're integrating an f of x g of y, something like that. Yeah, g of y dx. Okay, as long as it's in a product form, or it could be in a quotient form, like g of y over f of x, what you can do is you can separate. Oh, wait, the dx isn't there yet. Sorry. Oh, wait. Oh, Let me take all this back. I'm left-handed. I just forgot what I wrote. Give me a break. Let's pretend. Pretending's nice. dy dx equals f of x times g of y. Separable differential equations. Basically, it means move all the stuff with y's to one side, move all of the stuff with x's to the other side. So ergo the name separable differential equations. This one, rather abstract equations of f of x and g of y would become 1 over g of y dy equals, now notice we had to move the gy over. Well, on the other side, we've got f of x times dx. And this time we had to move the dx over. And then we can integrate both sides. And that's separable differential equations. And the one that's in play right here, the one that we just did the Euler's approximation, is a candidate for that. So let's set up. As far as the negative sign, I tend to leave it with the x. It does, I mean, technically it does not matter. So what we've got is dy dx equals negative y over x. This is a candidate for separable differential equations because the x function and the y function are both products or quotients of each other. So let's separate the variables. We've got 1 over y dy equals negative 1 over x dx. We're going to integrate both sides. What we're left with is the ln of y is equal to negative ln of x plus c. And this is a general solution. Actually, it's not a general solution because you got to solve for y. So, but this is the start of a general solution. It's at this point, since we have um, an X and Y, and this is an initial condition. Since we have an initial condition, we're going to plug that in. We're going to plug in 1 for X, we're going to plug in 2 for Y, and we're going to get the value of that constant. So we've got the ln of 2 is equal to negative ln of 1 plus C. The ln of 1 is equal to 0, therefore C is equal to the ln of 2. All right, so where we end up with this is we end up with an equation, the ln of Y is equal to the negative ln of X plus the ln of 2. Now, in order to evaluate this and solve, well, I'm sorry, to solve it for Y, we're going to have to exponentiate with E as our base. I would advise before doing that we collect these two terms together, and we can do that by writing it as the ln of Y is equal to the ln of 2 over X. All right, remember your properties of logarithms. When you're subtracting two logarithms, such as we are in this case, imagine I rewrite this instead as the ln of 2 minus the ln of X. When you're subtracting logarithms with a common base, you can rewrite the arguments 2 and X as a quotient 2 over X. Now it's safe to exponentiate with base E. And what we end up with is Y equals 2 over X. Okay, now remember with our approximation, we had Y was approximately equal to 1.5 when X equaled 1.3. Now we can see what the exact value is. If Y when X equals 1.3 is equal to 2 over 1.3, which equals 1.538. Okay, so this would be, see, this is one where when you're doing a question, if this were a multiple choice question, I could see this being represented as one of the answers. And if they ask you to do a Euler's method approximation, you better end up with 1.3. If you take the bait and just separate the variables, integrate, and evaluate, and you see they might put 1.538 as one of the choices, you've just answered the right, you've given the right answer to the wrong question. All right. So let me close out. I've given you a ton of stuff here. Let me close out with one last thing. Real quick, let's make a slope field of this. Okay, I think we did one in class. What you do with a slope field is you start to look for little patterns in the thing. Like I always look for what's going on when X and Y are both equal to 0. Either one is equal to 0. So if what's going on with 9-pen mode? Yes. dy dx when y equals 0. So we got X and 0. That's going to be negative 0 over X. Doesn't matter what X is. When Y is equal to 0, this thing always is going to have a slope of 0. So you would draw a bunch of tiny little line segments that have a slope equal to 0. Okay, now what's going on when, I don't think you're supposed to do this. The previous calc teacher at Redland and I had this conversation. dy dx, when X equals 0, well, we've got negative y over 0. This is undefined. And the way I would draw this, if I were drawing a slope field, I would draw a bunch of vertical lines right there. All right. And I think, as I recall, and you'd have to go to one of the more, I think it was about 2 years ago, they had a slope field question on the free response part of the test, and they gave you the points they wanted you to construct the slope field for. So all those points along the y-axis, as I recall, they weren't there. So they didn't let you draw a vertical line. So anyway, let's see. We need to fill in more stuff. So what about what's happening when x and y are equal to each other? So dy dx 1, 1. What I'm hoping you see is that the slope at 1, 1 is the same as the slope at 2, 2, which is the same as the slope at 3, 3. It's negative 1 over 1, which is negative 1. So we're going to draw a bunch of negative 1 slopes here, here, and here, and here. And what's going on when x and y are opposite signed? For example, dy dx at 1, negative 1. It's going to be negative 1 over 1, which is 1. So in all the cases when the x and y have opposite signs, we're going to have a slope of positive 1, or as best as you can draw a positive 1 slope. And there you start to see the makings of this. I think I'm just going to jump right ahead because we're about at time. Our original ordered pair was at 1, 2. So we've got, and it worked out to be an equation y equals x over 2. I think the path this follows is something like that. Okay, and that's part of a whole family of functions that are all arise from that as the differential equation. All right. Okay, that's as much as I wanted to get through today. If you guys have any questions, I think I offered you, if you wanted to do a U sub real quick, I could do one of those. Are we good? Put you to sleep. You guys ready for snow on Monday? I don't want us to be canceled again. Spending too much time out of school. All right, I'm gonna close. I'm not hearing anything, so I'm gonna get out of share.